Welcome to the Jack Westin MCAT Podcast with your hosts, Michael Maleka
and Molly Kilty. Hello, everyone, and welcome back to another episode of our Jack Westin MCAT Podcast with your hosts, Mike and Molly. In our last two episodes, we began our journey into the fascinating depths and black hole of brain science. We covered vital functions, right, on an evolutionary sense, what the brain first developed, the stuff that keeps us alive. And then we talked all about movement. Now, before we get into other brain and nervous system functions, we're going to take a little bit of a detour, okay? We're going to talk about something that has, you could think of it in context of the brain in terms of like EEG, alpha and beta and gamma.
Or
Waves.
Waves, right? You could think this. I was so excited when we were like doing this planning, when we were talking about the brain. We're like, wait a minute, we want to talk about some certain brain areas, but before we talk about these kind of sensations that are related to waves, maybe somebody listening, a few people listening knows what areas we're talking about. We'll talk about them later, but we need to actually discuss waves. And waves is such a fun thing to talk about because I just think anything physics people despise. Like I get it, right? There's math involved. There's like sometimes it's a little bit abstract, but some of this stuff is so interesting, especially because again, I love physics. Physics is so cool, and I know you do too, Molly. And so when we were planning out this episode, we were like, oh my goodness, there's so many things that are so interesting, but also so testable on the MCAT. And there's like especially a few points that we'll get to that again, you and I, Molly, when we were kind of like preparing, we were like, we need to talk about that thing. We were like, this is such a common mistake students make. So I'm very excited to talk about waves. So first, kind of go over what, a lot of people do know, the basic stuff, but also talk about how the MCAT tests it and what kind of pitfalls and traps you want to be looking out for. So we're talking about waves. I'm super excited to talk about it, Molly. I mean, as always.
Yes, I know. I feel like we say that every episode, right? So not just brain waves, right? We're talking about actual waves, longitudinal, transverse, light waves, sound waves, all of those good things. And of course, as part of our discussion, we're going to talk about things like hearing and eyesight. But you can't do that without understanding the physics. I know you love physics. I used to really not like physics. So you can learn to love it, and it comes down to understanding how it connects to the human body and how it can connect actually to your future career. So super excited. We're really going to get into the basics of how waves actually move, how they're transmitted, what they look like, etc. Okay, so, and again, this really stands at the interface of physics, bio, and psych. You can kind of see it in any section in certain ways. So it'd be pretty cool. Let's start out with just the basics of waves. Okay, so we talk about a wave. What are the parts of a wave that we should know? How can we see it visually on a diagram? What do you think? What's the basics?
Well, for me, I was like starting like, what even is a wave? Like, I feel like a lot of us can like see a wave and be like, yeah, that's a wave. But it's like, what are you actually seeing, right? When we talk about a wave is a disturbance of energy that transfers energy, not matter. Right? This is something that's very important, that it's just a disturbance that is transferring energy. Like when you see a wave in the ocean, for example, or you make waves in a puddle, right? If you actually track where the water molecules are going, the water molecules are just moving up and down. However, you can see the energy of the wave spreading out from if you have like a little puddle or a little pool, you like poked into it, it would spread out. Yet the water molecules themselves are just moving up and down. So it's not the water molecules that are being transferred, but the energy from the disturbance. So it's all about transferring energy. That's all a wave really is. And when we talk about waves, there's kind of like two types of waves, right? Like we have longitudinal waves and transverse waves, right? And while both of these are waves, they're kind of defined or kind of differentiated based on how the particles move compared to the direction the wave travels. So I like starting with the transverse wave because that's the one, like I think of ocean waves for that reason. The transverse wave is the one where the direction of particle movement is perpendicular to the direction of wave movement, or the direction of the wave is traveling. So in my puddle example, I dropped a rock in a puddle or dropped a rock in my bathtub. I don't know why I'm doing that, but I'm doing
Why are
that.
you,
I don't know. Maybe I don't know. Maybe
why do
they're
you have
cool.
rocks in your bathtub?
I like rocks. So, but let's say I dropped it in. While the wave would be spreading outwards, the water molecules are moving up and down. So while it's outwards and up and down, therefore they are perpendicular to one another. The direction of particle movement perpendicular to the direction the wave is traveling. Whereas a longitudinal wave, so that was transverse, a longitudinal wave, where instead of being perpendicular, they're essentially parallel to one another, or essentially in the same direction. Great example of that. And I think the universal example of a longitudinal wave is a slinky. I love the idea of a slinky, right? You have a slinky and you're kind of pushing it back and forth. You can see, right, the wave is traveling, right, across the slinky, right? But the spring parts are also moving kind of in the same direction as the wave. So because the matter is moving in the same direction, not in the perpendicular direction, that is an example of a longitudinal wave. So all waves either go into one of these two baskets. It's either transverse or it's longitudinal.
Yes.
Hmm.
And oftentimes when, I love the slinky example, I love the ocean wave example or the rock in your bathtub example.
I like rocks.
Um,
What do you want?
I think it's very common to actually imagine this in the context of the MCAT as light and sound, right?
Hmm.
And I think it makes a lot of sense, right? Especially when you think about sound, right? We know that there's not much that's actually moving. Sound can transmit through air. It's not that you are just like blowing air at somebody, right? Ultimately, when you are creating a sound wave, you are creating vibrations in the air, right? It's shifting them forwards and backwards as it's moving further away from you. And again, the characteristic of a longitudinal wave is that the vibrations occur in the same direction as movement, right? So that is what a sound wave does. Whether you're talking about speaking, whether you're talking about echolocation in a bat or plucking a guitar string, right? It's all just vibrations. We'll talk a little bit more about sound waves as well as light waves, which are the opposite kind, right? Those are transverse, and how they require media or not in a moment. But I think it's important before we move past our wave basics to just figure out what is the language we're going to use. Okay,
Hmm.
longitudinal, transverse, very important. But also each individual wave can be described by a couple different criteria, depending on, the source of the wave or what the wave actually is. So the first thing that I think makes the most sense is probably the wavelength, which is literally just the distance between two identical parts of a wave. Okay, so if you thought of an ocean wave,
Hmm.
right, you would be looking, probably the easiest is between the two crests, right? The highest displacement from that sort of central axis. You can take the two uppermost parts of that wave and you just ask what is the distance between them, right? How far are they separated, right? You could also take the two troughs, right? Or the lowest portion of the wave as it's oscillating. And that would be the same amount. You could also you can take at that central axis.
Hmm.
Just be careful.
You
And
have to
this
be
is something
careful.
students often do. You don't want to pick, one area that's in the middle, but on its way up, and one area that's in the middle, but on its way down, right? Two identical parts of the wave. Okay, that's a wavelength, and it's a distance, often in meters. You might see it in millimeters or nanometers,
Nanometers,
especially if
yeah.
you're talking about light. Um, and wavelength is going to be related to frequency.
Hmm.
Okay, and it's in hertz, it's 1/seconds. It's the number of cycles, right? So times that you go from one identical portion to a wave to the next per second.
Hmm.
So how many cycles are going on within a time frame? Okay. And you can imagine if you have a distance in some variant of meters and you have a frequency that's hertz or 1/seconds, what are you going to get if you multiply those two?
Okay, well, I got meters times 1/
Hmm.
seconds. Well, that sounds like a meters per second. That sounds like a velocity or a speed,
Sounds like a
right?
velocity. It
Right.
sure is.
And so that is how what we've just done is probably just found the most core equation to
Yes.
waves, which is the wave equation, which is the velocity of a wave equals the frequency times the wavelength. And velocity is exactly what you think it means. It's the speed of the wave. How fast is that wave traveling? And it's in meters per second. Now, I'm going to say something very, very important about this wave. V equals F lambda, right? It's from this equation that we know that if you increase frequency, lambda should increase. But let's think about what happens when you increase frequency on velocity. I ask this question all the time in like our free trial session, right? Like say you have V equals F lambda, you're probably listening to it now. You're like V equals F lambda, I got that equation. Say I increase frequency, what do you think is going to happen to velocity? If you're just taking it mathematically, okay, what do you think is going to happen to that velocity?
It's gonna go up.
It's gonna go. Everyone's like, oh, it's gonna
Frequency
go
goes
up
up.
for it, right? Because that's what it is. Absolutely not. Absolutely not. Velocity does not depend whatsoever on the frequency or the wavelength of a wave. Velocity only depends on the medium it is traveling in, right? If you increase frequency, wavelength's gonna go down. It's not going to impact velocity as long as you're in the same medium. And I can prove this. We can prove this, right? Because a lot of the times we talk about the different types of electromagnetic waves, like X-rays versus gamma rays versus visible light. They all have very different frequencies. But Molly, what do we know about their velocities?
It's always the same.
Always the exact same, right? Everyone always like, oh yeah, gamma rays are faster. No, they're not. Because although they have a higher frequency, their wavelength is lower and their velocity is the exact same. If you went to a new medium, on the other hand, now the velocity is going to change. But this is also something that's also important,
Yes.
right? So like we've gone now to a new medium, the velocity is going to change. But now V equals F lambda still needs to apply. So
Yes.
F or lambda has to change. Well, Molly, which one's going to change? Do both of them change? Neither, I don't know.
This I feel like was always so confusing for me, right?
Mhm.
You're used to regular proportionality, right? Like
Mhm.
if V changes, one of the other two have to change, maybe both change a little bit, right? Like how am I supposed to figure that out? If V, let's say, is decreasing, either one of them could be increasing, right? As long as that product is going down, that's all you need. But one thing that's very, very important to recognize is where the wave speed depends entirely on the medium, the frequency is determined by the source. Okay,
Mhm.
the frequency will not change. The frequency is always going to be the same, okay, depending on what created that wave. So, when we talk about wave speed changing, if we know frequency has to stay the same, what has to change is the wavelength.
Absolutely. So, and this is one question, like a lot of people overlook that idea. So, because some people like know the velocity depends on the medium. Some, not everyone, but now everyone listening knows. But a lot of times people overlook, oh wait, can frequency change after it's being produced? And the answer is no. After it's being produced, that frequency is going to stay the same, but that wavelength can change. Right? Another core property of a wave, other than the velocity, the frequency, and the wavelength of a wave, is the amplitude of the wave. Right? And this is related to, like, we talked about the crests, the peaks and the troughs, but they're related to how high that peak is from the central axis, like the tippy top of the peak, not like any other point, but it's like the highest or the maximum displacement from the central axis. That is what we call the amplitude. Now, the amplitude is very much related to how much energy that wave has. Because there's kind of two parts of a wave that we look at in order to see how much energy, because we talked about a wave is just a transfer of energy. Well, if we want to look at what parts of the wave tell us about energy, it's its amplitude and its frequency, right? Because if there's a more frequent wave, it's going to have more energy. It's happening much faster. Well, we also, if it has more amplitude, it also has much more energy. So it's both of these aspects that we want to look at for energy. However, amplitude, as shown in the equation, has nothing to do with velocity. The only thing that determines velocity is the medium, but V equals F lambda is the equation that will always, that's our wave equation.
Yes. And
Mhm.
sometimes you'll also see when you're talking about amplitude and how that impacts the properties of a wave, you may also see the word intensity, right?
Mm,
So let's take a sound wave, for
sure.
instance, right? If you had a high frequency, that would mean it's a really high pitch, like super high squeaky
Mhm.
sound, right? That would be high energy. Yes. If you had a high amplitude, what you would experience is an incredibly loud sound. Okay,
Mhm.
it's not pitch that's changing. Pitch is encoded by frequency. It would be the loudness of the sound. Okay, if we thought about light, which might seem a little bit less clear, right? The frequency is going to determine the color, right? If it's visible light. Um, but the amplitude will help us determine how bright it looks. Okay,
Hmm.
that's the intensity aspect. So yeah, it's super important to distinguish because, like you said, amplitude has nothing to do with frequency or wavelength. It's how big that displacement is. It's like how I don't want to say powerful. I mean, it is intense. How intense that wave is,
Hmm.
as far as how you experience it.
Yeah, yeah, no, 100%. And so once you know those bases of the waves, you understand the speed of a wave, frequency, lambda, and know that all waves follow these rules. All of the waves. There's not like, oh, this wave follows this one, this one. No, no, no. They all follow this universal principle. Then every single situation of a wave is just a new application of the same principles. And what we're going
Yeah.
to do is kind of like talk about some different applications of these. And I think the first one to talk about that, again, we're going to touch on more later on is sound waves, right? The kind of first example that I think is very important and very, very high yield on this exam. Right, this is kind of that example of the wave we were talking about before, but the longitudinal. You put it really wonderfully, Molly, where speaking is just putting vibrations in the wave. Therefore, sound is a longitudinal wave. But it's very interesting sound because these longitudinal waves are based on particles moving, right? Particles are colliding and then sending the next particle forward, then sending the next particle forward, then sending the next particle forward. And therefore, sound requires a medium. You need to have a medium in order to have sound because if there is no medium, there are no particles in the air. What's doing the colliding? There would be nothing to collide. And that's why, take space, for example.
Oh God.
There's no sound in space, right? And
That's so
that,
scary.
space, I love space. I think it's the coolest thing in the world. You're like, it's always like, oh my goodness, no sound. That is frightening. And I mean, yeah, no sound would be actually really frightening. But yeah, that's why there's no sound in space because there's no particles colliding. A kind of a note about these different areas. Like if you were to actually look at a longitudinal wave, you'll see areas where particles are really condensed together and areas of the wave where they're really spread out. Those areas of really that are condensed in area are called compressions of the wave, while the areas of a lot of space are known as rarefactions. If we were to translate a longitudinal wave to a transverse wave, the areas of compressions would be corresponding to like the peaks of the wave, right? Kind of the highest peaks. Whereas the rarefactions, where there's not a lot of particles, would be like the troughs of the wave. So it's in between those 2 points. That's where you're going to find your midpoint.
I love thinking about that because I
Mhm.
think that's so abstract for most of us. Is like, okay, well, I know how a transverse wave works. I think it's so much easier for most students to visualize. It goes up and down, it goes left to right, and you call it a day, right?
Mhm.
Longitudinal waves are, I think, a lot more abstract because they're showing vibrations. And if anyone has Googled a picture of what this looks like, it just looks like a bunch of lines, right? It's difficult to show unless you're looking at a GIF or a animation of some kind. You want it to be visible in the actual vibrations and movements. But it's cool that you can map it out and essentially show a longitudinal wave as if it were a transverse wave. And really it's the same idea. It's
Mhm.
just the direction that the particles are displaced that are different.
Mhm.
Um, and I actually technically temporarily displaced. It's the
Temporary.
direction
It's
the
not net. It's
energy
not
is
net
moving, is what I
displacement.
should
Yes.
say.
Yes.
Yes,
Yes.
technically. But I'm glad that you brought up my worst fear, which is getting lost out in space and not being able to, call for help.
Oh.
Um, because, because, right, it does need a medium. And I think you put it wonderfully, like it needs to vibrate through something. And I think this, as a younger sibling that was perpetually at the pool with my siblings, was the basis for like most of my childhood of like, go underwater and see how loud it sounds when you yell. Like, I'm gonna go underwater and like yell at my older brother and see how angry they get about how loud it is. And it all comes down to the fact that if you are sending vibrations, right, through a medium, if those particles in that medium are closer together, it's going to transmit better
Mhm.
because they can push against each other and transmit that sound wave, that vibration more effectively, right?
Mhm.
So, like, sound actually travels better in water than in air due to the
Mhm.
proximity of the molecules and the density essentially of the medium. And therefore, it actually travels better through solids as well than even in water. Which is very interesting. Again, it can't
Mhm.
travel in a vacuum because there are no particles, but the closer the packing is of those materials, right, the better that sound will actually transmit, which I just think is cool.
And because it's so like counterintuitive, sometimes you're like, oh, solids, right? That blocks sound. No, 100%. Yeah, obviously, right? But it's actually quite the opposite because, right, like you said, those particles are so close together, they can collide better. And therefore, the velocity of a sound wave in a solid medium way, way faster. Because like we said before, right, the velocity of a wave is determined by the medium. Notice how we never said anything about, oh, what was its frequency? What was its pitch? Because that didn't matter. That didn't matter for a sound wave. It only depends on what's the medium it's traveling through. Solid, faster, air, not as fast. Okay. Another great kind of like application of sound that's actually not verbal, which I think is kind of interesting, is ultrasounds. Ultrasounds are very, very cool and a very great application because you are using sound waves, but not for the purpose of hearing, which I think is interesting. Normally people are like, oh, sounds, hearing, duh, right? But actually with ultrasounds, what you're using is something known as the Doppler effect. Now, Doppler effect is a very interesting thing that occurs, but what it really boils down to is when two things are moving relative to one another, the perceived frequency changes. Because we said something very important. Oh, yeah, you're like, wait a minute. I see Molly's
Hold
shocked.
on,
Like,
wait,
wait a
the
minute.
frequency changes. I thought frequency never changed.
I
Mike,
knew
what's
you were
going
going
on?
to say. Right. What we said before holds true. Once a sound or a wave is produced, the frequency holds still. But with Doppler effect, it's all about the perceived frequency, right? Because if two objects are moving relative to one another, while the frequency might change the same, if I'm moving away from that object as it's producing the sound, I might perceive it as actually a lower frequency, right? Because I'm moving away from the wave as it's traveling towards me. So it's this idea, while I'll perceive it differently, right? It's actually the exact same, right? With ultrasounds, it's a really cool application because blood is flowing towards and away from the kind of probe. So based on if it's coming towards or away, we can actually detect the direction of blood flow based on the perceived frequency of the sensor, which I think is the coolest thing.
Yeah. Whenever I think of Doppler effect, it's one of my favorites to talk about because I worked on an ambulance, right? Like one of the most common like illustrations or examples in the real world of the Doppler effect is an ambulance siren, right? Like as the ambulance siren is coming closer to you, it sounds like the pitch is getting higher, right? Obviously louder, but also higher pitch. And it's because those sound waves are basically, because the ambulance is in motion, it feels like to your ears, right, that the frequency is higher. It isn't actually. And as soon as that ambulance passes you and it's now moving further away instead of closer, right, it sounds like the pitch drops quite a bit. The weirdest thing was when I started working on an ambulance, the pitch never changes, right? Like I'm so used to it. If an ambulance drives past you in a car or when you're standing on the sidewalk, you hear that difference in the pitch, right? Or in the frequency of that sound. But in reality, if you are not moving, like if I'm on an ambulance that's driving code 3 lights and sirens, it just sounds exactly the same. There's no Doppler effect. And it's because I'm in the ambulance. I'm in the back of the ambulance with my patient. It doesn't change the sound at all. And that I think for me was like, whoa, Doppler effect.
Whoa, Doppler. That's how
Now
I
I get it.
Right,
It's all perceived frequency.
exactly, right. The ambulance isn't actually going up and down when it's passing me, but like, oh, you're gonna hear it higher. Oh, you're gonna hear it lower. Right? It's all
Yes.
about, yeah, are you moving relative, right? You are not moving relative to the ambulance, so therefore it's gonna sound the exact same. So that's kind of
Yeah.
like a cool kind of Doppler. There is a Doppler equation to know, and I know a lot of students don't like the Doppler equation, but I would say join. I like go check out our question bank, right? If you want to get some practice using the Doppler equation, like you can literally go to the question bank, select, hey, I want waves and sounds problems, and you can actually go try out problems on the Doppler effect, on doing waves to actually apply the things that we're talking about, right? And so while practice with sound and understanding Doppler is good, there's another wave that the MCAT really also likes to test, right? Which is light, right? Or the electromagnetic waves. Now, light is, I feel like there's, when it comes to studying electromagnetic waves, we kind of, whenever we think light, I feel like we very much zone it down to the visible light, where it's like, oh, light is just the visible light spectrum. Because that's how when we say light, we're not talking about other ways. We're talking about, oh, Roy G. Biv. However, when we talk about light on the MCAT, it encompasses the entire electromagnetic spectrum, right? That's why we distinguish Roy G. Biv as the visible light spectrum, because that's what we can see. However, there's other light waves that we need to talk about. These are all electromagnetic waves, and light, like we mentioned, is a transverse wave. It goes up and it goes down while traveling left to right. There's the peaks and troughs. But light is also a really weird thing because while it's a wave, it's also its own particle, which is the
Yeah.
weirdest thing in the world, which I still to this day, I'm just kind of like, okay, I get it acts as both, but like visualizing that I think is so challenging. The fact that has
Yeah.
acts as both a particle and a wave, but understanding that acts as a particle is really important for a very important trait of light, right? Because it's a particle, it doesn't need any medium to travel, right? Where because like things like sound required the collisions of particles in order to transfer, but light's its own particle. It doesn't need anybody else. So therefore, light does not require a medium, while sound did. And that's because it kind of has this trait of being its own particle. It can kind of just travel on its own, right? And this also kind of like helps us understand where it moves best. Because if I'm a particle, do I want more stuff in my way or less stuff in my way?
I'm going to say, get out the way. I'd rather have nothing.
I'd rather have nothing. Absolutely. And that helps me to visualize, wait a minute, light moves best when there's nothing, when there's a vacuum, right? It moves best in a vacuum, the fastest in a vacuum, and then actually slows down when we get to like liquids and also solids, which is like the exact opposite of sounds, but also just makes sense when you understand what the differences are.
Yes.
Yeah.
Yeah, and light has so much going on with it. There's so many really interesting properties. There are some constants you'll want to know. Mostly it's the speed of light in a vacuum, right? 3 times 10 to the eighth meters per second. That's something you should know, right? You don't have to memorize every constant that's in every equation, but that is one that you should. You use it often. And it's an approximation technically, but 3 times 10 to the eighth meters per second, you're fine to use that. And we call that C. So just to clarify, you may sometimes see the equation we mentioned earlier, V times F times lambda, as C times F times lambda. Okay, if you see it,
Equals F
what did I say?
times.
Oh yeah, C equals F times lambda. Yes. And that would just be the same exact equation, but talking about the speed of light in the vacuum, which is pretty similar to speed of light in air. Not technically the same, but pretty darn close.
Yeah. And I love the kind of the transfer between it because again, it really comes back to the idea like the universal wave principles apply to all waves, right? V equals F lambda applies to sound waves. It applies to light waves. It applies to every wave. Sound, light, we just, instead of V, we put C because if it's traveling in a vacuum, that's its velocity. But the equation itself hasn't changed. So I think it's so interesting. And I love how we're also specifying it's in a vacuum. Right? Because if it wasn't in a vacuum, well, we know the velocity depends on the medium. So if it wasn't in a vacuum, it would change. Like if it's traveling through water, for example, it will not be traveling 3 times 10 to the 8 meters per second. It would not be, right? That's why we have to preface it's in a vacuum because speed of a wave, just like always depends on the medium. I always like stressing that so much because people always forget that idea, and I like to stress it. Just like in sound, right? I think you put it wonderfully how we determine like how we perceive the different properties of sound. Like we like higher frequency, different pitch, higher amplitude, different sound, like the sound intensity. Same idea with light. However, here, the frequency of a light wave determines its color. Right, higher frequency. If we're talking about visible spectrum, like higher, Like again, you're not gonna be talking about color at the non-visible one, but like if you're in the visible spectrum, it determines which type of wave. Maybe we can say in the electromagnetic spectrum, right? This is the difference between an X-ray and a gamma ray, or a UV ray and an infrared light ray, right? The difference between them is its frequency, thereby its wavelength, right? Because they're inverse to one another. Where the higher the frequency, that's when you get to, the gamma rays, X-rays, that sort of deal. Where the lower the frequency, that's when you're like microwaves and radio waves and that sort of idea. So the frequency determines, okay, which type of wave we have. Or the amplitude, like you said, is the brightness. How intense is it? I always like using this kind of example of like microwaves. Where if anyone's listening, like let's imagine, right? You put, again, this is gonna be very visual, so I'm sorry. Let's say you put, your head in a microwave. Would it last very long? Again, stay with me. Stay with me. Would it last very long? Would it be a comfortable experience? No, it's not going to be comfortable, and nor do I recommend anyone to do it. Right? Versus you and I, and maybe some other people are looking at a screen right now. Do we have any discomfort in our eyes?
No, not in the short term.
Not in the short term.
Long term, yes.
However, if you looked at an electromagnetic spectrum, right, visible light has a higher frequency and thereby more energy than microwaves. Wait a minute. Yet when I stuck my hand in the microwave, that's the one that cooked me. Yet I'm just looking at the screen right now and it's not cooking me. Like, what's that? Have we just broken physics here? Like, what's going on here, Molly?
When your head is in a microwave, I mean, I don't know how you'd close that up. I've got questions. That's all
Yeah.
I'm saying. Um, but I mean, I guess the question is, are we talking about energy as it relates to the energy of an individual photon or
Mm,
the amount of photons that you are experiencing? It comes down to the intensity, which
mm,
is related to the number of photons, which is the particle of
mm,
light. Or are we talking about the energy of an individual one, right? That's
mm.
when we talk about the E equals HF formula, which does, by the way, only work for light. It does not work for sound, right? You can't talk about energy with frequency of sound this way. So, I mean, is that what you're talking about?
That's exactly what I'm talking about. See, I knew we did not plan that out. I just thought it in my head and I just said it because I was like, this is such a great example because E equals HF is just for a singular proton. Because a lot
Yeah,
of people,
photon.
yeah, just for a single photon. Did I say photon? Oops. But E equals HF is just for a single photon, right? A lot of people have this kind of misunderstanding that E equals HF is the energy of light. It is not, because light, as we experience it, isn't just a single photon. We're experiencing so many photons. And the number of photons, the amount of photons we see from light, corresponds to its amplitude, right? When
Mhm.
people see E equals HF, they think, oh, the energy of light is only dependent on its frequency. And it is not. It's also dependent on its amplitude. But amplitude corresponds to the number of photons. More photons a light wave has, the higher the amplitude. But per photon, it's dependent on the frequency. Yeah, that I always use that example. I've used that example so many times. It's very visual. You're never going to forget it, right? But either way, I really want to preface, don't try to put your hand in a microwave. That's very, very unsafe.
Darn it. There go my plans for the
Please do
evening.
not, please. Hey, look at a screen, but also be careful. Be wary of your eyes, but don't do the first one. But I always like using that to kind of distinguish: are we talking about a single photon, or are we talking about a whole bunch of photons, which I think is a lot of fun.
Yes.
Yeah.
Absolutely. And I feel like it's important to recognize again that we think of light just in the visible spectrum, but there are many different wavelengths and frequencies, right, of light. So it's important to keep that in mind. It's not just the tiny little portion that we can see that's too human centric, right? You could talk about all different kinds of waves, radio waves, gamma waves, like you said, that have very different properties based on their frequency, especially and the energy that that creates. Um, let's talk a little bit. I mean, we know we'll talk about this in additional episodes as well, but what I'm very excited to get into in the rest of our sort of unit is how on earth can you take a wave and then create a neural impulse from that? Like, how can you take a vibration in the air and make an action potential? Or perhaps even weirder, how, because I mean, at least that in my brain is like, oh, that's physical, right? It could move
Mm-hmm.
stuff in its wake. How does light
Mm-hmm.
actually create an action potential, right? This is when we talk about sensation, right?
Mm-hmm.
And of course, we're talking about hearing and sound, or and hearing and vision. Um, and it's absolutely fascinating. We have specialized receptors that can actually pick up on these stimuli and convert them into action potentials. I, for one, am so excited to talk about
It's
this.
the coolest thing. Like when you like I don't know if you've ever seen The Matrix. Like have you've seen The
Mhm.
Matrix, right?
Yeah.
I This is a perfect example of like how if we just simulated the sensations, like if we just simulated the electrical impulses that our body has to real physical sensations, it's like we're experiencing life, right? Without experiencing it. That's the whole idea of The Matrix, right? You're getting the same physical sensations without the actual sensations just by activating the neurons. But in real life, right? We have these actual neurons that are responsible about getting the world around us. But that's why I think that's where from watching the Matrix, that's what really sparked my love for sensation because sensation is so cool that we can take, a sound, right, which leads to a hair cell bending, and that hair cell bending leads to electrical or an action potential, which leads to electrical signal to our brain, or our, in light, how we have our cones and receptors that when they receive light, there's a reaction that occurs, which causes ion channel opening and another action potential. How our body has adapted to receiving these waves is the absolute coolest. Now we're just brushing them on here because we're going to go so much more in depth in the next episode, right?
Yes.
So next episode, we're going to be covering all about hearing, right? We're going to break it up. We're not going to talk about hearing and vision in the same episode. Next episode, we're going to focus on hearing because I think there's something we need to also touch on first before we talk about vision. But we'll focus on hearing next episode, and then we'll continue on. I'm excited because the ear and hearing, super cool.
Oh yeah. I can't wait to talk about our auditory ossicles.
The ossicles, we love
The
that.
coolest named, tiniest little bones ever. Oh, it's so much fun. Yeah, we're gonna have a lot of fun with hearing. I for one absolutely cannot wait. This episode was fun, but I mean, hey, if
Okay.
you're hearing it, whether it's headphones, playing on a speaker, playing on your phone, whatever it is, you are enjoying the benefits of your hearing in some way, shape, or form.
Yeah.
So excited to talk about it.
Right. So until then, thank you all for staying until the end of the episode. Wherever you are, whether it's nighttime, daytime, you're on a bus, you're on a train, I hope you all have a wonderful rest of your day and happy studying, everybody. Bye for now.
Bye, everyone.